Discontinuity. Okay, a function. I also have a, sorry, before we go on to this function. So I did check all of my emails and all of my messages this weekend, but I haven't checked again today. So if I haven't written back to you, I'm going to do that this afternoon. So let's go. A function f is continuous. If the limit as x goes to a of f of x equals f of a. Okay, so an example. Let fx equal. It's x squared minus x minus 6 in the numerator over x minus 3. So we're going to factor that numerator to x plus 2 times x minus 3. We're going to graph this function. So you would maybe think to cancel, but if you cancel, then you lose this information here where x cannot equal 3. But overall, the graph does look like the line y equals x plus 2. It just has a hole at x equals 3. We'll write it all down and draw everything here. Okay. 1, 2, 3, the output would be 5. Well, I mean, if it were the line x plus 2, put in 2. Have that. Okay, go through an intercept of 0, 2. It's a straight line. Okay, so this domain is all real numbers except x cannot equal 3. And I see the question, we'll address that question in just a sec. Okay, all x in R such that x does not equal number 3. And then we talked about this kind of discontinuity. F of x has a removable discontinuity at x equals 3. And then I also noted that f of 3 is undefined. Okay, next example. Oh, actually, we want to stop and talk about the test. So let me think about it for a second. Nothing's really set in stone. Just want to have a plan. This is week 3. Next week is week 4. I think that this week we'll get through 2-6 and 2-7. Next week we'll start 2-8. Sorry, I'm talking to myself. I am thinking a good goal would be to post the test Wednesday, but go through a review Wednesday. and then have the test due the following Wednesday. You're doing it kind of like homework. It's a take-home test in a sense. And then we'll still cover some material, but if you have any questions on the test or the review, we can stop and talk about that next week. Okay, so I'm gonna write down that we want to have a test available Wednesday the 17th.
Could you explain the last part?
Yeah.
And could you explain the last part of it, the discontinuity part?
Yeah, you have a removable.
Like the removable discontinuity?
Yeah. If you, it's like any removable discontinuity is where you could redefine the function right at that place to make this continuous. So there's, if we put, if f of 3 equals 5, then f of x would be continuous. So if we could fill this in right here with just that one output that we were missing, now the function is continuous. Before I forget, that date was February 17th. And due, sorry, shaking, on the 24th. For exam 1. Also, this reminds me that I wanted to tell you that you can draw continuous functions without picking up your pen or pencil. So if I were able to, if I redefined f to have that 3 as have an output of 5, and then I can draw the graph straight through, it's continuous. I think that works. Okay. If you do draw the function and you have to lift your pen off the page and then go back to the page and keep drawing, there's a discontinuity there. Okay, on to another example. Okay, we will determine where h of x is continuous. Okay, h of x is 3 times the sine of x. Actually, it's a long function, so let's put this here. 3 sine of x plus x over x squared minus 4 plus the root of 49 minus x squared. And then I mentioned before that trig functions are continuous on, well, functions that are continuous on their domain include trig functions, rational functions, root functions. So we just need to check each domain. We're going to start here. This domain is all real numbers. It's a continuous function for all real numbers. this domain is all real numbers except for plus and minus 2. Then you'd have a 0 in the denominator. So domain needs to look like this. X in R such that X does not equal positive or negative 2. Okay, and then last one will fit down here. We're in the real numbers in this class, so this square root has to have something greater than or equal to 0 underneath it. You need a domain of -7 to 7. Try that really quick. Okay, so each time we're going to restrict the domain. First you have all real numbers. Now we've removed positive and negative 2. And now we're on the interval from -7 to 7. And also we need to take away positive and negative 2. So we put little holes right there. So let's write it all together. What we're writing is the domain, but we also know that we're continuous on this domain, so we'll put h of x is continuous on the interval from -7 to -2, include -7, not -2, union from the interval from -2 to 2, it's both open, and then from 2 to 7. I think. Close. It's continuous on that. Okay, so a sort of new topic, but we're still in the same section. Okay, the composition of functions. So just to like reminder, it's f composed with g of x, which is f of g of x. Okay. Okay, if you have something like ln of 9 minus x squared, the outer function is ln of x, and the inner function is 9 minus x squared. Inner function g of x minus x squared. The outer function would be like f of x equals okay. Here's a theorem. if f of x is continuous at x equals b, well, hang on. If f of x is continuous at, I'm just going to put b, so it's not confusing. The limit as x goes to a of g of x equals b. The result, I have to check it out. It's like the limit as x goes to a of f of g of x. Okay, so we'll bring this limit in, have f of the limit as x goes to a g of x. This limit as x goes to a of g of x was equal to b, so this is equal to f of b. And now we can practice examples. First example. There's space. Little space. The limit as x goes to 2 of ln of 9 minus x squared. 9 minus. Ln of 9 minus x squared. So what we'll do is do ln of the limit as x goes to 2 of 9 minus x squared. This is a polynomial, so we can put 2 in for x and get ln of 9 minus 2 squared. So I got ln of 5. So label like okay, next example. Limit as x goes to, well, this one's a little interesting. So we're going to 3 from the left. Wait, minus sign. Minus sign is from the right. X goes to 3. ln of 9 minus x squared. Okay, we'll bring the limit in. Okay, we're going to 3 from the left, but still, you're going to, what am I trying to say? No, we need to draw. I need to draw this up. I'm trying to say something that doesn't make sense. Okay, that would be the right side. Here's the left side. So some number a little bit smaller than 3. Then you're going to square it. So something just a little less than 9. 9 minus a number just a little bit less than 9. So this is a very small positive number. Okay, and then your function ln. We have this x value becoming 0, so you're going closer and closer to 0 for x, and ln is going down to negative infinity. Yeah. Hopefully that makes sense. I've got next example. It's the limit as x goes to 3 of sine of pi x over 2. Okay, so we'll take this limit in here. The sine of the limit as x goes to 3 of pi x over 2. Okay, that was like a linear function, just x times pi over 2. So I'm going to put in 3 for x. And I got -1. All right, next one is a little tricky, but it's the limit as x goes to -1. Oh, sorry. And e to the power x squared plus 2. So the outer function is e to the x, and the inner function is x squared plus 2. So when I put the limit in, it goes up into the power. Bring the limit in. E with a limit as x goes to -1, x squared plus 2. Okay, x squared plus 2 is a polynomial. Yes. -1 squared will be 1. Add 2. E cubed here. All right, I think that's probably the last example. So the other part of this theorem is about the composition of functions being continuous. G of x is continuous at x equals a. F of x is continuous at g of a. Then f of g of x is continuous at x equals a. So my example is determine where h of x is continuous. And h of x is ln of cosine of x. Okay, so first, let's see, if g of x is continuous at x equals a, my inner function g of x will be cosine of x, and f of x will be ln of x. So first we want to figure out where the inner function is continuous. Then we can tell where the outer function is continuous. And then we'll be done. G of x is cosine of x. And f of x would be my ln of x. Cosine of x is a trig function, so it's continuous on its domain, which is all real numbers. For ln of x, graph. So vertical asymptote here, what's this? Y is any number, so x equals 0. Comes up and over. So this will be continuous on its domain, which goes from 0 to positive infinity. So for the composition of those functions, h of x, we will need cosine of x to be greater than or equal to 0. Actually, strictly greater than 0. We're not going to equal 0. We're just going to keep on getting closer and closer and closer. Let's go back up here and draw cosine. Okay, go down, let's do another here. Roll one cycle at 2 pi. This is pi over 2. Negative pi over 2. This is 3 pi over 2. We are positive between negative pi over 2 and pi over 2. Then from 3 pi over 2 to 5 pi over 2. So that's going to happen for the set. Picks up at negative pi over 2 and goes to pi over 2. Union with the set from 3 pi over 2 to 5 pi over 2. Union, dot, dot, dot. I was trying to fit one more, but we'll write it like this. Go negative pi over 2 plus 2k pi. to k pi or pi k. Either way, I put pi k. And then pi over 2 plus 2 times pi times k. And k is an integer. Okay, and that's the set where h of x is continuous. So let's put it here. Okay, so h of x is continuous on this set. I think I have explained that enough. So we also talk about the intermediate value theorem, and then that's it for this section. We'll draw a couple pictures for this theorem too. It's something we're not going to prove. It's something we want to just apply and use in like our homework or in practice. Okay, here we go. If you took a higher math class, you might prove this in like 130, definitely in 230. But for now, we just want to use it. Okay, if f of x is continuous on AB, and n is a number between f of a and f of b, capital N, then there exists a real number c. Actually, let's write then there exists c, and it's in this set, the open interval from a to b. So we're going to put c exists in the interval from a to b. C exists in the open interval from a to b such that f of c equals n. F is continuous on AB. So I'm going to draw like a generic continuous function. Let's do
Professor, what does that say next to parentheses AB?
parentheses. Oh, this
Like it says
is this one.
yeah, that part.
This is exist. I got startled. But that's
Uh,
so if I put x exists in R, means x exists in the real numbers. We could also write like this. There exists a less than C. It's the same thing. Okay, our function is continuous. Let's do f like this. Let's put A. This here is f of A. This doesn't look very nice. Let's put it here. Okay. I'm going to put you back. Let's do n is some number between a and b. We'll put it right here. So f is a continuous function, and let's see, n is a number between f of a and f of b. Then there exists a real number c. Right here. Such that f sends c to n, or f of c equals n. Oh, let's do another picture. Yeah, no, please ask questions. I'm just not used to Zoom, but I'll get used to it. Okay, we've got function. It's going to go like this. Let's call this A, and this is going to be B. F of A is here. Ish. F of B we'll put here. And then I'm going to pick n to be like right about there. Just n is some number between f of A and f of B. The theorem, the intermediate value theorem, gives us a number c. We're going to call this actually c1. Such that f of c1 equals n. Or you could pick this one, f of c2 would equal n. Here, that could be called c3. Here, c4. Here, c5. c6. c7. So the theorem says that there exists at least one, but maybe there's more. Like this one had 7 different values of c that satisfied the intermediate value theorem. Okay, let's use this thing. Show roots. Show that a function has roots. All right, we want to show that cosine of x equal to x has at least one real root on 0, 1. show cosine of x equal to x. One real root on the interval between 0 and 1. So the first step is to write this equation as a function that's equal to 0. So where we're looking for our roots. Okay, so we'll just subtract x from both sides. That way cosine of x minus x equals 0. And we'll let f of x equal cosine of x minus x. Okay. So we're going now to the interval 0, 1. So, I put a note to show that f is continuous. We need that part for the theorem. So we need f to be continuous on the interval from 0 to 1. Cool. So I put that, well, we could just write it out. Your function looks like this. And from last time, we know the functions that are continuous on their domains are trig functions and polynomials. So this domain is R. This is continuous for domain equal to same here. This one's also continuous. It's just a straight line. Domain is all real numbers. Thus, if it's continuous on R, it's going to be continuous on the interval from 0 to 1. Okay, so we've got that our function is continuous on 0 to 1. Let's find f of 0 and f of 1. The cosine of 0 minus 0 would be 1 minus 0, and you get 1. Make sure. Cool, just check. Cosine of 1, subtract 1. This number is negative 0.4597. Okay, so I have a note that f of 0 is a positive number. It's greater than or equal to 0. So we've got f of 0. And 1 is a negative number less than 0. Oh, we're almost out of time. So we'll finish this up and then call it good. So apply the intermediate value theorem. So that y equals 0, or should I put capital N equal to 0? I'm going to stick with y equals 0. It's between f of 0 and f of 1. Then. There exists a number c in the set 0 to 1 such that f of c equals 0. In other words, f has at least one real root. So I'm going to put thus f. I'm going to put thus cosine of x equal to x has at least one real root on 0, 1. Okay, so we're gonna stop. Class time's over, but we made it to the end of 2.5. So next time we'll talk about 2.6.